So we continue toward working to a way to evaluate this function, this integral, without too much trouble. So we still need some more pieces. So another important piece of background is, what if I have, let's just look at some of these things geometrically. So let's say I look at the area from A to B in relation to the area from B to C. All right, so the area from A to B, I'm going to make B green. I guess that's green. All right, and the area from B to C, I'm going to make that be pink. All right, so this area from A to B, all right, that is the integral from A to B of f of x dx, whatever the function xf is. And these are just definitions based on area at this point. The area from B to C is what we mean by the integral from B to C of f of x dx. And then I also have the total area going all the way from A to C, and that's the integral of from A to C of f of x dx. So now that we are interpreting this integral as an area, we can make some geometric assumptions about it, or conclusions about it. So for example, the integral from A to C of f of x dx is equal to the integral from A to B of f of x dx plus the integral from B to C of f of x dx, which is a complicated way of saying something fairly simple. The big area, the whole thing, is equal to the green area plus the pink area, right? So that should be kind of obvious. Right? This is our green area right here, the integral from A to B. This is our pink area, the integral from B to C. All right, so I think they call this something like the integral addition theorem or something, but it's hardly worth noting, giving a name to. All right, but what I do want to do is rearrange this a little bit. And so I can figure out, for example, that the integral from A to C, I'm just going to subtract integral from A to B from both sides. Integral from A to C of f of x dx is, minus the integral from A to B of f of x dx is equal to the integral from B to C of f of x dx. All right, so that's just saying if I take the big area and I subtract out the green area, then what's left is the pink area. Right? So the big area minus the green area is equal to the pink area. So that's geometrically makes sense. Algebraically, it's just moving this to the other side. Sorry about the little mess here. That is a minus sign. All right. So what? Well, I'll tell you what. So here's what we're going to do now. I'm just trying to decide if I should flip the page first or not. I think I am going to. All right. So maybe I'll keep that page. No, I guess I can't do that really. All right. So we're going to now define a function capital F of x. And what that function is going to be is the integral from a to x of f of t dt. All right. The t is a dummy variable for little f because I want to use x as the independent variable for the function capital X, f. Capital F. So the picture that goes with that function definition is this. I have a function little f, all right? And if I go from A to some point x, and I look at that area in here, then the area is what is meant by capital F of x. All right. Now what I've done is make x the independent variable so it could move back and forth, and I'm interested in how the area changes with a change in x. So if I'm interested in how it changes, that's a derivative. So we're basically saying, let's take this new thing that we just figured out, the integral, and throw into it the thing that we already knew, which was derivative. Can I talk about what df dx is, the derivative of this function as the x changes? Well, the t is just a dummy variable that is like the t's are sort of in here, if you will, and the x is the upper limit. It's playing the role of what we used to call b. All right, so how could I get a handle on the derivative, the rate of change of this with respect to x? Well, go back to your limit definition of the derivative. The derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. That's the limit definition of the derivative, right? So in this case, what that means is the limit as h approaches 0 of, what is integral of f of x plus, what is capital F of x plus h? Well, according to our definition up here, capital F of x plus h is going to be the integral from a to x plus h of f of t dt. Watch all the crazy variable changes here. And then my f of x is going to be the integral from a to x of f of t dt. By the way, this is very much wizard behind the curtain stuff. You'll never have to do this. The result that we're going to get is going to be spectacularly easy, but you need to know where it comes from. My denominator is h. All right, well, what the heck am I going to do with that? Well, I just came up with this useful idea, which is that, so this is why I was debating whether to keep this on the same page. I think I'm going to go ahead and tear this page out. That's what I sort of didn't want to do, but I will. All right, since the integral from a to c of f of x dx minus the integral from a to b of f of x dx is the integral from b to c of f of x dx. See, this is our ac, this is our ab, so the c is the x plus h and the b is the x. So I can subtract these integrals and get the integral from b to c, which is going to be the integral from x to x plus h. All right, so that equals the limit as h approaches 0 of the integral from x to x plus h of f of t dt over h. All right, now this thing has kind of an important meaning. So as I'm looking at changes in x, so if I move over a distant h and I get to the point x plus h, then that integral from x to x plus h is the exact area from x to x plus h if I make a small increment h. And of course, since the limit is h, so I'm taking the limit as h approaches 0, I'm looking at this increment gets smaller and smaller. All right, so that's that. And then, let's see, where do we go from there? Oh, I got that. All right, so I could rewrite that as the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt. All right, that's just pulling the h out to the front. So why do I do that? Why do I care about that? Because in this integral, a is x and b is x plus h. So b minus a is x plus h minus x, so it's just h. So that 1 over h is 1 over b minus a, right? So that 1 over h is really 1 over b minus a. And we just had this nifty theorem about 1 over b minus a times the integral from a to b of f of x dx being equal to f of c for some value c that is in a of b. It's in the interval from a to b, but we just don't know what that c is, all right? But what we can say is that 1 over h times the integral from x to x plus h f of t dt equals f of c for some c in the interval x plus h. That's the mean value theorem for derivatives. The 1 over b minus a integral a to b of f of t dt equals f of c. That's, look again at that integral mean value theorem for integrals. All right, so now what's going to go on? I'm taking the limit as h approaches 0 of this function right here. I want the limit as h approaches 0. So a sort of, maybe I should go to the next step before I talk about sort of how that works. So it works like this. If I want to look at the limit as h approaches 0 of this integral, that's then equal to the limit as h approaches 0 of f of c for some c that is in the interval x plus h, right? So, this is what we're saying here. This part of this integral is equal to f of c, so I can just sub that for that integral. All right? Now, so what is going on with this c? The c is in between x and x plus h. So if we look at the x, since c is in x and x to x plus h, c is less than or equal, x is less than or equal to c is less than or equal to x plus h. The c is in between x and x plus h. All right? But we're taking the limit as h approaches 0. the limit as h approaches 0. So now look, isn't this that same sandwich theorem layout? I have some unknown value that lies between two values that I understand very well. In fact, this x and x plus h, they're just the left and right-hand side of an area that I could approximate with a rectangle from the left and from the right. But I could also approximate it at the magic point, which is in between. So in a certain sense, that C is in here. C is in here. And it's a rectangle whose area is the exact area matching the pink area. All right, so the C is in here in between x and x plus h. And if I build a rectangle out of that, that area is going to be exactly equal to my added on area. That's what it means that this integral from 1 over h times the integral from x to x plus h of f of t dt can be replaced by just f of c. All right, where the c is in between the x and x plus h. Now what's happening is h approaches 0. What does x approach as a limit? X just stays x. X plus h, since the h is approaching 0, also approaches x. Therefore, the c must also approach x. All right, so what's really going on here is if you think about an approximating rectangle that has a left side and a right side, and remember we said before, as the delta x is approaching 0, or in this context we're calling it h, as h approaches 0, that the left and the right end up being the same point. Well, that point c was trapped in between them. The c has to be in between the left and right hand of the interval. So that's also the same point. When we take all these limits as h approaches 0, the left hand, the right hand, and c are all the same point. They all can be called x. So one way that I can conclude this is to say that I have the limit as h approaches 0 of f of c. That's what df dx is equal to. Let's bring that back to see where we started. df dx is equal to the limit as h approaches 0 of f of c. And I've just shown that c approaches x. So this is equal to I'm going to put it this way. It's equal to f of the limit as h approaches 0 of c, and c approaches x, so it equals f of x. Now, this astounding and weird fact is often known as the fundamental theorem of calculus part 1. So it's saying that df dx, which remember that was the derivative with respect to x of the integral from a to x of f of t dt, is just equal to f of x. All right, that's the crucial thing. So that means that capital F prime of x is equal to little f of x, would be another way to say that. All right, so what's really going on, see the derivative of the integral gives you the original function back. Derivative sort of undoes the integral. So another way we can say that is that the integral and the derivative they act like inverse functions, right? F inverse of f of x equals x. But integral and derivative, you can call them functions, but when we have functions whose domain and range are other functions, we often call them operators. So we can say integral and derivative are inverse operators. And a crucial way to say this is that the integral is the antiderivative. And so a lot of people use the words antiderivative and integral interchangeably, right? So we can say the integral from a to x of f of t dt, we can now sort of get a handle on what that is. It's equal to capital F of x, where capital F is an antiderivative of f. That is to say, capital F prime of x equals f of x. All right, so this is a conclusion that's sort of interesting. This part right here is called the fundamental theorem of calculus part 1. So we call that fundamental theorem of calculus part 1. By the way, some books will interchange the two parts. but we abbreviate this FTC1. And this is how the AP material always categorizes it also. They call this part 1. But I've seen books where they call this one part 2, and the part we're about to get and call part 2, they'll call part 1. All right? So by itself, we're not yet to something that allows me to quickly do a definite integral. But we're almost there, and this video is running long, so I'm going to cut to the next video.